Hello everyone, I hope you're doing well. In this video, we'll be seeing the free particle in quantum mechanics. That will be a 1D case. Okay, we'll be considering the one-dimensional case because this video is a part of lecture series when we are considering the topics that are considered in the beginning level of quantum mechanics. Okay, it is like we are just introduced to quantum mechanics and we are considering some of the system, and I must tell you that the free particle is the simplest system in quantum mechanics. So we'll be considering and having the quantum description of free particle. Alright, before that we have seen that how a free particle behaves in classical mechanics, but now we want to consider it in quantum mechanics, and we want to see that what is the wave function that describes a free particle, how we can calculate that wave function from Schrödinger's equation, and which Schrödinger's equation will be used, the time independent Schrödinger's equation. And after that we'll get some of the observables like energy, momentum and position using the wave function that we have derived from the Schrödinger's equation. Alright, so we'll have a complete overview of the free particle in quantum mechanics, and with that being said, let's quickly get started with the topic. And first of all, we should know and describe what the free particle is, what free particle means. And as the name suggests, we can see that a free particle is a particle that is free of any restrictions, forces or potentials. There is no external potential that acts upon this particle. There is no force that acts upon this particle. So such a particle which is free of that is not experiencing any potential or any force is said to be free particle. Okay, and as we know in Schrödinger's equation, we have that potential term. So, and we'll connect the free particles definition to potential. We'll use the potential word here because we know that Schrödinger's equation is used to describe and find out the wave functions for the systems in quantum mechanics. So Schrödinger's equation have the word potential in it. Okay, we know that the Hamiltonian term has potential energy term in it. So we'll define and describe all different kinds of systems in and their cases in terms of their potential. For example, a case where V is equals to 0, a case where V is equals to V naught, and so on. Okay, we always categorize systems on the basis of the potential the system experiences. It's because in Schrödinger's equation, we can see the potential is the defining term that separates one system from another system. So let's quickly get started with defining the free particle. And a free particle is the simplest one-dimensional problem. If it's 2D, you'll write 2D problem. Okay, if it's 3D, you write 3D, because out of all the dimensional problems, free particle problem is always the simplest one because it incorporates the zero potential energy term, and that makes the problem really simple. In quantum mechanics, with V equals 0 everywhere. Here we can see the word everywhere, and it was added here intentionally to show that there are the cases where we see the free particle in a box. Okay, the free particle in a box, it means that the particle is free only inside the box, and it's not experiencing any force only inside the box, and it will experience outside of those boundaries. But here, the case that we are considering, that particle is free everywhere from minus infinity to plus infinity over all space. Okay, this particle is free over all space from minus infinity to plus infinity, since it's one dimensional. So from minus x to plus x infinities, okay, along x dimension. So this particle is free everywhere. There is no exception on where it's free and where it's not. All right, so this is the kind of case we have. And other than that, now we know the potential, and now we need to select which Schrodinger's equation to choose. Like we have time independent Schrodinger's equation and time dependent Schrodinger's equation. So how you are supposed to decide which Schrödinger equation to use? This is the point that most of the professors doesn't make clear to the students, that how to decide and what central thing decides which Schrödinger's equation to use. Okay, and that central point is potential. You'll see what is potential equals to. Okay, and if potential is dependent upon time, then you are supposed to use the time dependent Schrödinger's equation. Okay, the one that depends upon time, that incorporates the time variable in it. If potential doesn't contain any time term, if it doesn't contain any time term, let's say it's not e to the power iota t, or it's not equals to v is equals to e t a, or doesn't contain any time variable in it, then it means you are supposed to use the time independent Schrödinger's equation. Such potentials are independent of time, they doesn't change with time. So we can see here the potential that we have in here is v equals to 0, and it doesn't contain time term. Okay, and v equals to 0 means v of x equals to 0. Okay, we can have that this thing, like we can write it like that. Okay, v as a function of x equals to 0 to show that it's one dimensional potential and it's 0 everywhere, and we can see it's independent of time, so we'll be using the time independent Schrödinger's equation. And there is one interesting fact about the time independent Schrödinger's equation and the wave functions that it results. It's that the time independent Schrödinger's equation applies for the potentials that are independent of time, and besides that it results into states which are stationary. Okay, it results into stationary states. What does stationary states mean? Stationary, the word itself means the states which are stationary. Stationary means that are not changing with time. Okay, so they results stationary states. You must have seen this word, that it generates stationary states. The free particle wave function represents stationary states, and it represents a plane wave. We'll see that what does plane wave mean later on, so we'll have that description later on. So for now you should know that how we have decided that we will be using the time independent Schrödinger's equation. Now let's mention this. Since v of x equals to 0, the potential is time independent, so we will use time independent Schrödinger's equation to determine the wave function representing the free particle. Okay, free particle. Let's mention the time independent Schrödinger's equation in here, and I hope you will remember that it's minus h squared by 2m, and we'll use partial square by partial x square because it's 1D case along x dimension. So partial square by partial x square plus v of x into psi of x. Okay, the wave function dependent upon x, that is equals to e times psi of x. If you have seen that video that I have done to derive the time independent Schrödinger's equation, you must remember one thing, that was that we separated psi, the main psi, into two parts, psi of x and psi of t. That is the psi of x here, and psi of t was calculated in that video, and we'll utilize it later on in this video as well to demonstrate some of the facts about the free particle. I'll make that point clear later on as well. I was just mentioning it so that it is in your mind that it will be coming later on. And this is the time independent Schrödinger equation, and for free particle we'll put v of x equal to 0 in here. So let's plug that value right into here. M is the mass of the free particle. Okay, you can mention here m is the mass of free particle. Partial square by partial x square plus 0 into psi of x equals E times psi of x. E is the energy of the free particle. E represents the energy state of free particle. So we are left with minus h square by 2m partial square by partial x square. This psi of x multiplies here. This 0 just vanishes and we are left with this equation. Now what else we can do is to partial square by partial x square psi of x. We can take these terms right here. Here we are solving actually the differential equation. So I'm taking 2m here. It will be multiplied 2me divided by h square. It's multiplying here. It will be divided here. Negative sign in here and psi of x. Now what else we can do is that this thing is negative in here. We will take it to the other side and it will become positive. It's being subtracted on the other side, so it will be added in here. So we are 2m capital E by h square psi of x equals 0. That is this equation so far, and here I'm gonna let something here. We have 2me by h square, so let 2me by h square is equals to k square, and I'm doing it so because this quantity has a units of per meter square, and if you take under root this per meter, which is the wave number, okay, it has the units of wave number. That is why we are letting it to be equals to k square, because this quantity, this 2me by h square, if you evaluate the units of it, it is per meter square, which means it has, if we take under root of it, it will have unit of per meter. All right, so it means it represents the wave vector. That is why I kept it equals to k square, where we'll mention that where k is a wave number. All right, so let's plug that value right here. So we have some simplified form, k square psi of x equals to 0. Now I'm gonna use, I will call it as equation number 1, and I'm gonna use a technique in solving the differential equations like this, and that is a kind of technique that works in most of the cases. You should learn these techniques because when you are given a problem, you can't write the solutions directly, and mostly you are unsure about this outcome that is, that is coming. So you should know the method to solve such differential equations, and for that purpose I'm gonna let psi of x is equals to a e to the power iota m1x. I'm using m1x because here we have mass, so you should not confuse that mass with that number m1. Here m1 is a random number. I'm just supposing it to just for the sake of solving this differential equation, and it is not mass, it is something else, it's just a number, and I'm gonna call it as equation number 2. And we know we have psi of x here, we can plug it here, but we should have this double derivative of psi of x as well. So we are supposed to calculate the double derivative of psi of x. Let's calculate it. Double derivative means partial by partial x, then partial by partial x again of psi of x. Let's find out the derivative of this exponential, and a is constant, it will come out, and derivative of exponential is that exponential comes as it is, then derivative of its power, which is iota m1x. I'm taking this a here because it's constant. Derivative of this term iota m1 is constant, so we can write here. Then we have partial x by partial x, which is equals to 1. So we have a, I'm taking iota m outside as well. We have m1x. Okay, let's take its derivative again. which will be again the same thing. That will be iota m times e to the power iota m1x. So it's iota square m square e to the power iota m1x. It's m1, sorry. It's m1. And iota square is equals to -1. We know that. We'll write it. Since iota square equals -1, so it's minus a m1 square e to the power iota m1x. That is the double derivative of psi of x. Let's plug these two values into equation number 1. Minus a m1 square e to the power iota m1x plus k square a e to the power iota m1x equals 0. Here we can take a e to the power iota m1x as common. So we are left with minus m1 square plus k square equals 0. And we can take this to the other side, so it becomes 0, and we are left with this term. Now we can take k square to the other side. It's positive here, it will become negative here, so positive minus minus cancels out. m1 square equals k square. Taking under root on both sides, we get m1 equals plus minus k. This k square and under root cancel, so we have m1 equals plus minus k. So we have got two values for m1. One is positive, which is k, and the other is negative, which is minus k. So we got two values for m1. From 2, we had psi of x equals a e to the power iota m1x. Alright, and we have got two values of m1. One is positive and one is negative. So the solution will split into two parts. One with a positive, m1 positive x, and the other with a negative e to the power iota m1 negative x. Let's insert the value of n plus and n minus, which is k, and here it's minus k, into this expression, and it's iota kx plus a minus in subscript. It's just to show that it's the constant for this negative solution expression. That is the wave function, space dependent wave function, to describe a free particle in one dimension. And this is the positive part and this is the negative part. It shows that this is the wave traveling in the positive direction, or that's the positive direction, and this shows the wave traveling in the negative direction. And the free particle is described and equals to the superposition of wave traveling in positive x direction and a wave traveling in negative x direction. We'll have the description later on as well, but we need to write down the total wave function for the free particle in 1D box. And sometimes in most of the cases, tutors just stop there. Okay, they doesn't proceed later on. So we'll write that this is the space dependent because it is dependent upon the x variable. And in quantum mechanics, we say that the time dependent and space dependent means that it is depending upon x, y, and z variables, while time dependent means that it is depending upon time. So this is the space dependent wave function for a free particle in one dimension. All right, and a plus e to the power iota kx represent wave traveling in positive x direction, whereas a minus e to the power minus iota kx represents a wave traveling in negative x direction, which is left. You can choose whatever notation you like. Negative x direction. The free particle wave function is the superposition of particle wave function is the superposition of both. waves. All right, so we have this situation now. Superposition means that linear combination, and linear combination means sum of these two quantities multiplied by some constants. Okay, and now next we are gonna write the total wave function for the free particle in quantum mechanics. Now we know that the total wave function for time independent states is given by psi of x and t equals psi of x and psi of t. Now we are having a moment of truth. Okay, at this point of derivation, I want to address one of the major misconception and misunderstanding most of the students have towards the time independent states. They think that the time independent states, or wave functions we can say, are completely independent of time. They doesn't have any time dependence or factor in them. So that's not the case. Let me clarify, okay, and let me justify here. The wave functions we have seen in the derivation of time independent Schrödinger's equation. If you have watched that video, I'll link it in the description box. So in that derivation, we have seen that we assume that the wave function is separable. The wave function, which is changing with x and t, can be separable into space part and the time part. Okay, and that's the first assumption that we had towards the time independent states. And the second thing was that the potential is independent of time. These are the two major assumptions that we made to establish and derive the time independent Schrödinger's equation. Okay, and while derivating the time independent Schrödinger's equation, we saw and witnessed that we had calculated psi of t as well. Okay, there were two equations that were resulted. One of the equations were the Schrödinger's equation that we saw earlier in this video. Okay, that is one of the Schrödinger's equation, and this Schrödinger's equation, time independent Schrödinger's equation, gives us the psi of x. Okay, while the other equation that we had established while derivating the time independent Schrödinger's equation was this psi of t. Okay, and its solution was calculated, and you don't need to calculate it or derive it every time. That's something that is true everywhere. Okay, whenever you are considering the time independent Schrödinger equation, then the time dependent wave function will always stay the same no matter what. So it was equals to a e to the power iota e by h cut t negative. All right, so that is the time dependent wave function, and it stays the same no matter what. Okay, and here e by h cut is actually equals to omega. If you know the formula, the Planck's formula, which is hf. Okay, in terms of h cut, we can write it equals to h cut omega. Okay, so e by omega will be equals to h cut will be equals to omega. So we can write this equation as a e to the power minus iota omega t. Okay, that is the time dependent wave function, and it's always a part of the total wave function that represents the system which is under a time independent potential. All right, so here we also talked about the stationary states. So as I told you people that such systems do not evolve with time, then what does that mean? If the wave function is changing with time, then why I said in the earlier statements that time independent Schrödinger's equation gives us the stationary states, and why the system is stationary if it is evolving with time. So let me clarify. We'll prove it later on that, and we have also seen in the fundamentals of quantum mechanics that psi itself is complex. Okay, and a complex quantity cannot represent realities. All right, while we saw that psi square actually represents a real quantity, it's always a real quantity, and it's actually something that represents the system. not psi but psi square, the square modulus of psi. And we'll prove it here using this wave function, this total wave function, that when we calculate psi square, it is independent of time. It doesn't have time dependence. All right, so the thing that is describing reality is psi square, and we'll prove it later on that psi square is always independent of time when we are considering the potentials or systems which are under time independent potentials. All right, so that is how we say that such systems are not evolving with time and such systems remain constant with respect to time. Okay, so that is what we mean. It's psi square that is significant and holds some meaning in quantum mechanics, not psi but psi square. All right, so keep that in mind and don't don't just delve into that misconception that the wave functions, the total wave function, is independent of time. No, that is not the case. And since psi of t remains the same, and since that is why it's always significant to calculate psi of x, because it's the only thing that is different. Psi of t is always this for the time independent systems. Okay, for the time independent potential, for the systems which are under time independent potential, this is always psi of t. You don't need to calculate it. You have done it during the derivation of Schrodinger's equation. You don't need to do it again and again. Okay, that is the point. And we have to calculate psi of x, which is different for every system. That is why we are interested in Schrodinger's equation that we wrote this way at first place, and that is how we just reached this form. Okay, and that is the form that we are most interested in. I hope you got the point and you got the significance of psi of x, that why we are always calculating psi of x and we are not focusing on psi of t. We most of the time directly write this into the solution, and we directly write this total wave function. Okay, so I just wanted to make you people understand that was the basic case. We always have the wave function in a total wave function that has time dependence and x dependence. In those wave functions in which the time dependence and space dependence could be completely separated from each other, are the separable wave functions. And when these separable wave functions are under time independent potentials, they give rise to stationary states in which the probability density function is independent of time. We'll see and prove it later on, but yes. Okay, I hope I have made everything crystal clear here and you don't have any confusions and questions. And even if you have any, you can ask me in comment section. So let us proceed from this point onwards and see what kind of solutions for total wave functions we get for the free particle. Okay, and we'll discuss the other things meanwhile. Where let's write what is psi of t. Psi of t is equals to a is some constant, and e to the power minus iota e by h cut times t. And as I told you people earlier, that e by h cut is actually omega, which is angular frequency, so we can write it as iota omega t. All right, so that is it. We know that psi of x is equals to this. We know psi of t is equals to this. So let's put these values into this total wave function. This is the total wave function. So let's do that. I think this location is better. So let's insert the values. And psi of x is a plus e to the power iota kx plus a minus e to the power minus iota kx. And we have psi of t to be equals to minus iota omega t. All right, so let's multiply it with these values. It's a plus a e to the power iota kx e to the power minus iota omega t plus a minus a e to the power iota kx minus e to the power minus iota omega t. Here we can see a plus is a constant, a is a constant, it results into another constant. A minus and a results into another constant. We can call them as b plus e to the power. Now the bases are same. You can see the bases are same. Base, what does base mean and what does exponent mean? We have always a term called as base, to which raised to the which there is an exponent, let's say t. Okay, so that is called as base on which the exponent is landed. Okay, you can see that this base is carrying this exponent, so anything that is at this position is exponent, and the one that holds it is the base. So we can see the base is e here and the base is e here. So when two different terms have same base, we can see this is e and this is e as well, powers can be added. Okay, because they have same base, they become friends and they can share each other's exponents. So it's iota kx and it's minus iota omega t. So we have added them. Similarly, here we can replace it with b minus e to the power minus iota kx. Similarly, here the bases are same, so the exponents could be added. I'm constantly using this term like b plus and b minus just because it makes it so obvious to write down that statement that one of them shows the wave traveling in the positive x direction and the other shows, the negative one shows the wave that is traveling to the negative x direction, just to make it, you know, obvious. That is why I'm using this sign. You can use a1, b1 to c1 or whatever. Here further on we can take iota common, so we can take iota as common, so we are left with kx minus omega t plus b minus e to the power, we can take minus iota common, kx plus omega t. That is the total wave function. This is the total wave function for a free particle in one dimension evolving with time t. All right, the energy of this free particle is given by you must remember that we assumed that k square equals 2me by h cut square. You must remember it at first place when we just assume that, and we can take h cut square here, h cut square k square, and 2m is multiplying here, so it will be divided here. That is equals to e. E was the energy eigenvalue in Schrödinger's equation, so we can see that the energy of a free particle is equals to h cut square k square by 2m. Okay, where m is the mass of free particle. M is the mass of free particle and k is its momentum. All right, and we can also determine the momentum of free particle from this equation, and the momentum of free particle is h cut k. We will prove it later on, but let me write it right there. So if the wave is considered, if this wave is considered, it's positive h cut k. If this wave is considered, then it's negative h cut k. Okay, it depends upon in which direction the particle is moving. If it's moving in the positive direction, it will be positive h cut k. If it's moving in negative direction, it's negative h cut k. Okay, if we calculate the uncertainty associated with energy and momentum, using the formula that I have mentioned in previous video. I'll prove it in later video, but we are just mentioning all these things to have a certain argument about the free particle system in quantum mechanics. Okay, I'm building an argument. You will see what argument, what kind of argument it is. So with energy and momentum, then we see that delta E equals 0 and delta P equals 0. This means that the energy and the momentum of a free particle is exactly known. Okay, and hence the uncertainty associated with its position and time, position and time goes to infinity. That is, delta x approaches to infinity and delta t approaches to infinity in accordance to Heisenberg's uncertainty principle. If we know energy of a particle exactly, then we have lost information about the time of the state of a system completely. Okay, it means that if the uncertainty in energy is 0, then the uncertainty in time goes to infinity. If the uncertainty in momentum is 0, then uncertainty in its position, about the position of a particle, is lost. Okay, so that is what we are saying here, and we can prove it from this statement that delta E equals 0, delta P is equals to 0, that is given by its mathematical calculation. Moreover, we can also reinforce and confirm that statement by calculating the probability density corresponding to the positive plane wave and the negative plane wave. Actually, I didn't tell you before, but such waves which have this kind of solution are called as plane waves. Okay, they resemble a plane wave in classical mechanics. These waves are known as plane waves, and this is the wave traveling in positive direction. This is the wave traveling in negative direction. And if you are considering a particle can be either moving in positive direction or in negative direction. If it's moving in positive direction, then this is the wave function that represents that particle. If it's moving in negative direction, this is the wave function that represents that particle. So it's either this or this, and since both of the possibilities are possible, that is why we write them as a superposition state. Okay, and when we are finding out the probability density, or when we are finding out the normalization constant, we'll take each solution separately, not the whole of it. Okay, it's because it's only one state at a time. All these chunks are separate and they have separate existence, but when we are considering the whole system, then we represent them as the linear combination of all the states, all the possible states in which it could be present. So when we represent wave function as a linear combination of different wave functions, then all these wave functions should be separately normalized. Okay, don't mix it with the fact that we will add them up and we'll normalize this wave function. No, all these linearly independent wave functions should be separately normalized. Okay, they are linearly independent solutions, they are completely different from each other, and they doesn't have anything interfering with each other, like it's completely different, this is completely different. Okay, so we'll normalize, or we'll find out the probability density of each of these separately. Let's write it. Moreover, the probability density of psi of xt is given by, so let's consider the positive solution, psi plus x of t, I'll consider it plus square, and that will be equal to psi plus x of t star, and psi plus x of t simple one. O star could be written here. Psi plus x of t, the simple wave function, is actually b plus e to the power iota kx minus omega t. That was the positive plane wave, right? And conjugate of it is actually obtained by replacing iota by negative iota. So this iota will become negative iota. That is how you will obtain conjugate of a wave function. Next, let's see the product. B plus is b plus square, and let's here we have e and this is e. They are being multiplied with each other. Bases are same, you can say. See, bases are same, so exponents will be added. Okay, that is the rule in exponents. What does base mean? Base mean the quantity which holds the power, which holds the weight of power. So this E is the base over which this power is dancing. So that is base and that is base. So bases are same, so they become friends and they share the weight with each other. So it's E same and the powers will be added, and it's iota kx. I'm multiplying minus iota inside, so it's minus iota kx, and minus iota into minus omega t makes it plus iota omega t, and this power, it's plus only, so nothing will change, only iota will be multiplied inside, so minus iota omega t. We can see here that minus omega t plus omega t cancels out, minus kx iota plus iota kx cancels out, and we are left with b plus whole square. That is the probability density function, which is equals to a constant quantity, and this constant quantity doesn't contain x or t dependence, which means that the probability density function is independent of x and t. That is what I said before, but let's calculate it for the other chunk and we will have some words on it. The probability density function for the function for negative solution, or we can say psi minus x of t, is psi minus x of t, and that is equals to psi minus star x of t times psi minus x of t. That is equals to, we have psi minus to be equals to b minus e to the power minus iota kx plus omega t, and star of it will be like, it's minus iota, right? We'll change iota by minus iota, so it's minus minus plus, so it's plus iota. So here we'll write plus iota kx plus omega t. We'll do the same thing, it's b minus whole square, this one square, and bases are same, powers will be added, we'll multiply iota inside, it's kx plus iota omega t, and here we'll multiply minus inside, so it's minus iota kx minus iota omega t, and we can see that it's cancelled out, and it's e to the power 0. E to the power 0 is actually equals to 1. The similar thing happened before, and we can see here that this probability density function is also independent of x and t. Okay, so we can write that psi plus minus x of t at once if we want to write them together. It's plus above and minus below. It's b plus minus whole square. We can see that the probability density is independent of time, hence the state psi of xt represents a stationary state. Alright, and the probability density function is independent of time, of x, which means that the probability density is constant everywhere, and it leads to the fact that psi of xt plus minus couldn't be normalized. The normalization condition ensures that the total probability of finding a particle is always equals to 1. It's not greater than that, but this wave function cannot be normalized. All right, because if we do so, the integral goes to infinity. We'll write this sentence only, that integral goes to infinity as follows. We can see how the integral goes to infinity. The normalization condition is actually, let me write the integral here. This is the integral of normalization condition. Since the free particle is free everywhere from minus infinity to plus infinity, so the integral will go from minus infinity to plus infinity, and we have this term like that. We take the integral of probability density function from minus infinity to plus infinity. Since this is equals to plus b plus minus whole square dx, which is constant and doesn't depend upon x, so we can take it outside of this integral, and we are left with e to the minus infinity to plus infinity dx, and this integral diverges. Okay, if you find out, it is actually this, and this is not defined, this is actually infinity, so the integral goes to infinity. Such wave functions are not normalized. They cannot be normalized. Saying so, we can say that a free particle system in a quantum mechanics has many anomalies when we consider its plane waves or the wave function that we have calculated before, since that wave function is not well behaved. When we are considering the wave functions in Schrödinger's equation, we have developed some rules for the well behaved wave functions, and one of them is that the well behaved wave functions, they are normalized, they can be normalized, and they could be square integrable. Square integrable means that this integration of normalization constant is not infinity but some real value, some positive real value. And we can see here that this condition is not satisfied by the wave function of free particle, which is free everywhere. Okay, that is the problem that this wave function or system presents, and this problem is eradicated by considering the concept of wave packets. Okay, hence the wave function of a free particle cannot be normalized and is not well behaved wave function, and does not represent and does not represent a well behaved wave function. Hence, we have seen two of the anomalies with the system of free particle. One of them is that they cannot be normalized. They does not represent a well-behaved wave function. And the another anomaly that we have seen is that their position and time uncertainty goes to infinity. All right. So I have discussed these two anomalies in here. There are the other two anomalies as well, that the group velocity and the phase velocity, there is a huge difference in between them. So these are the kind of problems that exist in such a system. I'll mention here the solution, that how they are, the problem is eradicated by the concept of wave packets, but I'll not mention the details of it. I'll mention its detail in a later video, because as a beginner you shouldn't be that much into it. Okay, that is not required, and if you need that, I'll make a separate video on that. Let's close this video by mentioning all of these facts. and we are not supposed to prove them right now. The free particle wave function are unphysical because physical wave functions are square integrable, which means that the probability density function and its integration over whole space is a real constant or real number, and it is never infinity. Okay, so that is what we mean, are square integrable. Hence we can see that the momentum and energy of a particle shouldn't be precisely defined. We can see that the problem that we cannot normalize the free particle wave function, and the problem that it's unphysical, they all root back to the fact that the energy and the momentum were accurately defined. If they were not accurately defined, then this problem could be solved, and we can do so by having a concept of wave packets, where what we have is that we have a ton of waves, they superimpose each other, and they result into a wave packet, a packet of wave that has some momentum, which has some uncertainty associated with it, and it has some position with some uncertainty associated with it. Okay, that is how we solve this problem. And we have seen that the same problem existed in case of matter waves, and the concept of wave packet eradicated that problem, and it involves the superposition of waves of different momenta. Okay, we assume that there are a ton of waves that make up that particle, and all of those waves, all of those chunks have slightly different momenta, and they add up to give a small chunk. Okay, and which have some uncertainty, non-zero uncertainty associated with it, and the problem gets solved. So let's write this down, and the problem will be solved. We can construct a physical solution by means of a linear combination of plane waves, which is actually these waves that we considered before, called as resulting wave packets. All right, the concept of wave packet eradicates all of the anomalies with the free particle system, because we can see that the free particle are localized. We can see where they are. So that's not the real case. Okay, that's not something that brings us closer to the reality. So what brings us closer to the reality is the concept of wave packets. So from having those problems, we led ourselves towards the actual case that represents the free particle. Okay, it's actually the wave packets that represents the free particle exactly. First, the position and energy of wave packets are not exactly known. Or we can say momentum and time as well, because they relate with each other. And only probabilistic outcomes are possible. When uncertainty is non-zero, then we talk about probabilities. That was the probability that the particle has this position, what is the probability that particle has this energy. When we say that this particle has exactly this energy, it means that we know for sure that this particle has this energy, and we are not talking about probability. Then if you're talking about something with certainty, it means that the concept of probability vanishes, because probability is associated with uncertain things. All right, so that is how we are saying that when energy and position are not exactly known, then probabilistic outcomes are possible. And yes, that is what we needed to represent a system that is feasible in quantum mechanics. We know in quantum mechanics that nothing is certain, everything has probabilistic outcomes. So that is what we needed to achieve. The speed of wave packet is given by its group velocity, which is actually equals to momentum over mass. Whatever its momentum is divided by the mass. And thirdly, wave packets are normalizable. So all of the issues has been resolved. It means that a free particle, therefore, a free particle cannot be represented by a single wave, a single plane wave. Instead, a wave packet represents a free particle. The physical solution of Schrödinger's equation for a free particle are represented by wave packets. Not the plane waves or the stationary states. Okay, so those stationary states doesn't actually represent the true state of a free particle, but the wave packets represents the true state of a free particle. Okay, which involves the superposition of all those plane waves that we got. That involves the superposition of all different plane waves with slightly different, which involves the superposition of all those plane waves with slightly different momenta decay. Okay, so that is it for this video. I hope you got it. And the similar problem arises when we are considering the matter waves. In case of matter waves, we saw that the group velocity is actually equals to the velocity that we see for the particle in classical physics, but the phase velocity that represents the velocity of a single matter wave is greater than the speed of light, and that was a kind of problem, and that was eradicated by the concept of wave packets as well. And they said that it's the group velocity that matters, and actually the grouping matters, the wave packets matter, and it's the wave packet that represents the matter and free particle as well. So that is it for this video. I hope you got it, and we'll see that how to calculate the speed of the free particle, but that was not necessary to be added here. I'll do it separately. And yeah, like, share and subscribe. Goodbye.